Yeah, welcome to VLSI Simplified YouTube channel. So today I want to explain about this shift registers, how to write the program in shift registers, Verilog code for the shift registers. Okay, so shift registers. So in digital, we already seen in the shift registers, you have four types of shift registers. Those are serial in, serial out. Okay, and next is serial in, parallel out, parallel in, serial out, and parallel in, parallel out. Okay, parallel in, parallel out. So these are the shift registers we have. So that means in serial in, serial out, the data will be loaded serially, and data will be taken serially, one bit. Okay, that is serial in, serial out. And so that means if it is like n bits, it will take 2n minus 1 clock cycles to get the data. Okay, and SIPO means that the data will be inserted serially. Okay, and whatever the data that will be taken at a time. Okay, and parallel in, serial out means data will be loaded parallelly, and it will be taken out serially. Okay, and parallel in, parallel out means here data will be inserted parallelly, and data will be taken out parallelly. Okay, it will take one clock cycle. Okay, so we'll discuss this. So first method is first we'll see the SISO. Okay, serial in, serial out. So in serial in, serial out, just you have, like, if you are using 4 bit of data, if you are using 4 bit of data, so you are using 4 D flip flops. So you are using 4 D flip flops. So these 4 D flip flops are connected synchronously. So common clock for all the flip flops. Okay. So common clock for all the flip flops. So common clock will be given. This is positive edge trigger, positive edge trigger, and these here you can say like D naught, next to Q naught. Okay, and it is given to D1, Q1, and D2. Okay, next to Q2. Okay, Q2 and D3 and Q3. Okay, so Q3. So you can means we can write the program for D flip flop. Okay, so we can write the program for D flip flop, and D flip flop as a top module. We can do with the normal structural modeling. Okay, so structural modeling we can do. That is one method to write the program. But we'll discuss how to write the program for the behavioral modeling. Okay, so behavioral modeling, we'll see how to write the program for the behavioral modeling. Behavioral modeling. If you see the behavioral modeling in the SISO, so I will do with the left shift operation. So if it is left shift operation, let us take you are giving 1111 to SISO. Okay, so that means how it will do, like so initially the output of all flip flops will be 0. So this is index value 3210. Okay, 3210. And first clock cycle. So this is the initial clock cycle. First clock cycle, one bit will be inserted, and these 3 bits will be shifted. Okay, so these three bits will be shifted. You are getting 000. So this will be shifted like this. It will be shifted like this. At second clock edge, what happens? One bit will be inserted, and this will be shifted. So here you are getting 1, here you are getting 0, and here you are getting 0. Okay, and at third clock cycle, one bit will be inserted, and this will be shifted. So one you will get here, and one you will get in here, and here 0. Okay. So at fourth clock pulse, all the serial data will be loaded. Okay, and from fifth clock pulse onwards, you can take the bits from the third bit of this one. Okay, this is the that means at seventh clock pulse. At seventh clock pulse, whatever the bits are there, that will be come out serially. Okay, so that means we can say that if it is n bits, so it will take 2n minus 1 bits. Okay, 2n minus 1 bits to get the data. Okay, 2n minus 1 bits to get the all the bits of data. Okay, so this is the basic operation of SISO. So if you see the SISO, so basic if you see the behavioral modeling, so basic block diagram, if you see, okay, internally there will be 4 D flip-flops. So what are the output inputs for this SISO? So this is SISO. You have the input clock, okay, and next you have reset pin, and one more that is serial in bit. So this is 1 bit. So this is 1 bit, and next you have serial out. Serial out is also 1 bit. Serial out is also 1 bit. Okay. So I want to write the program for this left shift operation, that is shift register. Okay. So if you see, so I'm writing the program for code for SISO. Code for SISO. Serial in, serial out. So first I will take a module SISO 4 bit. So initialize the inputs. What are the inputs? Input clock, okay, and next reset, serial in, and output is serial out. So you consider output you can consider as a reg serial out. As this is a behavioral modeling, you need to consider that output as reg. So reg serial out. So I need to initialize some temporary register, that is reg 3 down to 0, 3 down to 0 temp, 3 down to 0 temp. Okay, so always at the rate passage of clock, always at the rate passage of clock. Okay, passage of clock. So when positive edge of clock is occurring, okay, this is predefined word, passage of clock, begin. So if reset, that means if reset equal to 1, if reset means what? If reset equal to 1, so temp is initialized to, so here you're going to use non-blocking operators in the sequential circuits, 4 tick binary, 0 0 0 0, okay, 4 zeros, okay, else, okay, else, so temp equal to, you are using concatenation operator. Okay, you are using concatenation operator. So for the left shift, 1 bit is what? From the left you are adding the data serially, so that means you are adding the data serially. So here you can write serial in. Okay, serial in, and here, mm, here what you will get, like if you see in the previous operation, so that means if you see, so every time this is shifted, so these bits are shifted, and this is coming to 3 to 1. Okay, 3, so this is come to the bits of next bit, that means 2 down to 0 bits are shifting, and it is coming to the next bit. Okay, anyway this bit is what? Serial input bit. Okay, so if you see the second clock cycle, 2 1 0, so the index values of 2 1 0 are shifted, and it is coming to the left side. Okay, it is coming to the left side. If you see the second clock cycle also, 0 1 1, it is shifted, and it is coming to the next side. So that means here you can say, you can write this is what this is you can write temp, what is the index value? 2 down to 0, 2 down to 0. Okay, temp 2 down to 0, and next here I am writing, so continuation. So this is left shift. So this is left shift. Okay, left shift. So if you see like so end, and next assign serial out, serial out. So from a, where you are taking serial out, that is if you see serial out, you are getting from this. So at last you loaded the data at 6th clock pulse, you are getting the serial out. So that means this will be shifted. So that means here you are getting 1 1 1. So vacant position is loaded with 0. So here at temp 0, you are getting the serial out. Okay. So that means you can write so serial out equal to what? Temp 0. Temp 0. Okay. And end module. Okay. So this is the program for SISO. Okay. So this is a program for SISO. Suppose if it is a right operation, so right shift. So how to do? So right shift, change the color. There is only one change in this. Okay. 1 second. Low I will take. Okay, see here. So if it is the right shift, so what happens? This is 3, 2, 1, and 0. Okay. So from left side, you are loading the data. So that means initially all the inputs are 0, 0, 0. This is at initial clock cycle. At first clock cycle, 1 will be loaded and this will be shifted. So that means this will be shifted and you are getting 0, 0, 0. Okay. At second clock cycle, so at second clock cycle, one will be added, loaded, and this will be shifted. Here you are getting 100. At third clock cycle, one will be added, and this will be shifted. You are getting 110. At fourth clock cycle, you are getting one, and one will be added. So at fourth clock cycle, all the bits will be added. Okay, and at last, at fifth clock cycle, so you are getting the serial out at 0th bit. Okay, so the only change. So this is left shift. Suppose if it is right shift, here I can write, okay, if it is right shift, I can write temp equal to what? Temp equal to temp is so here I need to use non-blocking statement. Uh, so so you are inserting the data serially. So that is serial in, serial in, comma, and here what we can write. So that is serial in, comma. So you're serially inserting the data and temp temp that is 3 down to 1, 3 down to 1, temp 3 down to 1, and here that is for right shift. So here assign assign serial out, serial out is what? Serial out is temp temp here okay. So if it is serial in it is temp 3 now. Temp 3. See, serial left shift means temp 3 and right shift is temp 0. Okay, right shift is temp 0. Okay, you are taking the values from the temp 0. Okay, so this is nothing but serial SISO shift register for right shift. Okay, left shift and right shift. Okay, suppose if you want to write the test bench for this test bench for SISO, test bench for SISO. So module SISO underscore 4-bit TB. Okay. Declare the internal variables. Declare the internal variables. Okay. What are the internal variables? We already see reg. That is so inputs for the test bench we need to take as a reg, clock, reset, and a serial in. Okay, serial in. And output for the test bench we need to take as wire. Okay, wire, serial out, serial out. Okay, and next is step 2. Step 2, instantiate the design in the test bench. Okay, instantiate the whatever the design you did for the SISO, you need to instantiate the design in test bench. Okay, so two methods are there. One is uh, so that means instantiation by name or instantiation by position. Okay, so here I'm using instantiation by position. So whatever the position of inputs and outputs I given, So like that should be same value SISO 4 bit and DUT clock reset serial in serial in serial out serial out. So by position I am giving the values, okay, instantiating the values, okay. So this is by position. Port values I am giving by positions, instantiating the this CISO by position. And the step 3 initialize the variables, initialize the variables. So you need to initialize the variables to 0. So that means so multiple statements are there, means you need to use initial begin, so clock reset and serial in so equal to 0, okay, and end, okay. So this is step 3. And next step 4 generate the clock, so we are using always you are giving 5 hash 5 clock equal to negation of clock, okay. So that means clock will start from, so initially clock is 0 for how many time units, 5 time units, and clock becomes what, clock becomes 1 for next 5 time units, okay. So that means total clock period, so let us take from here to here, it will take how many time units, so it will be repeated for always, so that's why I given always, it will be, so for one time period. So that means what is the clock period for this one, this is, it will take 10 time units, okay. And the step 5 step 5 I need to drive the stimulus, that means I need to give the text vectors, okay. So driving the stimulus, okay. So initial begin, so at the rate negate of clock reset equal to what, reset equal to 1, okay. So why are you giving negate of clock, means in order to overcome this setup time and hold time, we are giving the at negate of clock, okay. So if you are giving at passage of clock, if your output is changing at that passage of clock, you will get the violations of setup time and hold time, okay. And this is negate of clock reset equal to 0, okay. And next at the rate negate of clock. So how many values you are giving? 4 values I am giving now. Serial in, that is equal to what, 1, okay. And next at the rate 4 times you need to give. So at the rate negate of clock, and serial in equal to what, equal to 1, okay. So like this 2 more times at the rate negate of clock, serial in equal to 1, and the same at the rate negate of clock, serial in equal to 1, okay. And next end module, okay. So this is the test bench for CISO, okay. So test bench is common for all the sequential circuits, okay. So this is the test bench, I think you have seen, you understood. Next is we are going with SIPO serial in parallel out, okay. So serial in parallel out, so I'm changing the color, okay. SIPO SIPO is nothing but serial in parallel out. Okay, so that means for serial input data, it will consist of suppose 4 bits of data I'm giving. So for serial input, you want 4 clock cycles, and for parallel out, you need 1 clock cycle. Okay, total it will take 5 clock cycles to get the data. So if you see the like if you see the basic block diagram for this CISO, so you have clock as input, and next reset, and you need to give serial in. Okay, and there is one more input, that is load. Okay, and next, so serial in is one bit data, parallel out parallel out parallel out is this is 4 bit of data, 4 bit data. Okay, so I want to write the Verilog code for this SIPO. Okay, so you see module module SIPO. So what are the inputs? Input, clock, reset, serial in, and output. What is output? Output, output, parallel out. Parallel out is the output. Okay, parallel out, and here you need to consider output. This is you need to use 3 is to 0. 3 down to 0. Okay, 3 down to 0. Why? Because we are getting parallel out as 4 bit, no? So that's why 3 down to 0, and you need to use initialize this reg. Output is reg. So here reg 3 down to 0. 3 down to 0. I am initializing some temporary register temp. Okay, always always at the rate passage of clock, begin. Okay, if reset equal to 1, temp value is initialized with all zeros, no? 4 tick binary 0000. Okay, 4 tick binary 0000. Else else, okay, same left shift. So for left shift, here I'm writing, so for left shift, so that means temp, previously I've seen, no? So this is equal to what? That is temp 2 down to 0. So this will be shifted. That means whatever the shifted data, that will come in the next bit, and serially you are inserting the data. So serial in. Okay, serial in. This is left shift. This is nothing but left shift. Okay, and assign assign parallel out parallel out. Okay, so parallel out equal to temp. Okay, parallel out equal to temp, and end module. Module. Okay, so this is the Verilog code for SIPO. Okay, so Verilog code for SIPO. Next, PISO, parallel in parallel out. So parallel in parallel out. Okay, so if you see PISO, so this is PISO, parallel in serial out. Okay, this is parallel in serial out. So you have clock, next reset, and next you have load, and you have parallel in data. So parallel it means what? At a time you can load 4 bit of data. Okay, 4 bit of data, and serially you need to take out the data bit by bit. Okay, so this is parallel in is how many bit? This is 4 bit. Okay, and next serial out is only 1 bit, only 1 bit. Okay, so there is a signal called load. Okay, so in the PISO, this is PISO, sorry, PISO. parallel in, serial out. Okay, so PISO, we see a signal called load by shift bar. Load by shift bar. Okay, load by shift bar. So when load by shift bar equal to if it is 0, it will do which operation? Shift operation. Okay, means it is active low signal, shift bar is there, no? So when load by shift bar equal to 1, it will do what operation? Load operation. So we can load 4 bit of data. So same like that, we have a signal called load. Okay, so when load equal to 1, which operation it will do? It will load the data. So whatever the data, so that will be parallel bit data is there, that will be loaded. Okay, and when load equal to 0, it will do the shift operation. It will do the shift operation. Okay, so we'll see this program. Okay, program for this PISO. Okay, PISO module PISO input. What are the inputs? Input, clock, reset, and input I need to give separately. 3 to 0, parallel in, parallel in, and next one more load, input load, and output reg serial out, output serial out. Okay, so I'm initializing one temporary register reg 3 to 0 temp, 3 to 0 temp. Okay, so always at passage of the clock, always at the rate passage of the clock, passage of the clock. So if reset equal to 1, temp equal to what? Just you are initializing the output of all the registers. So 4 tick binary 0000. Okay, temp value is 4 tick binary 0000. And else else if, okay, load, else if load means what? Load equal to 1. So if load equal to 1, you need to load the temp with what data? Parallel data. So that means parallel in, 4 bit of data at a time you need to load. Okay, else if load, so load equal to 0. Okay, else if load equal to 0, what you need to do? You need to do the shift operation. So you need to do the shift operation means same as left shift, we already seen, no? So 3 2 1 0. Okay, so that means already 4 bits of data are loaded. After that you need to do the shift operation. So that means here this one will come 1 and this one will come 1. Okay, so this shifting 1, and whatever the vacant position is there, that will be loaded with this one. Okay, at first clock cycle, the next first clock cycle it will be loaded, and next this will go out. Okay, and this one will be shifted. Okay, 1 1, and next 0 0. Okay, next 1 0 0 0. Okay, after that 0 0 0 0 you'll get. Okay, so from this you can write the logic, that is temp equal to what? Temp equal to so that will be shifted, that means temp. So what will be shifted? That is these values are shifting and it is coming. So 2 is to, so 2 down to 0, I can write temp 2 down to 0, comma, whatever the vacant position is there, that will be loaded with what? 0. So here you can write 0. Okay, temp equal to temp 2 down to 0 comma 0. Okay, so next end assign assign serial out, serial out. So from where you are getting serial out? Serial out is So from temp 3 means at the index value of 3, you are getting the serial out. So I can write this one as what temp 3. I can use the temp 3 and end module, any module. So like this, we can do the PISO operation, parallel in serial out. Okay. So there, while designing, you are using mux. So for the mux, you are giving as a selection line like load by shift bar. So depending on the selection line, when load by shift bar equal to 1, it will do the load operation. When load by shift bar equal to 0, it will do the shift operation. Okay. And last one is PIPO, parallel in parallel out. Okay. So parallel in parallel out. Okay, PIPO. So if you see the PIPO, so whatever the data is there, you are loading parallelly, and the data you are taking parallelly. So one is clock input, so input is clock and reset. Okay, and parallel in data, so this is 4 bits. So this is 4 bits, and you are taking out parallel out, so parallel out. So this is also 4 bits. So within one clock cycle, you are inserting the data and you are taking the data out. Okay. So for this, I want to write the program Verilog code module PIPO parallel in parallel out. Okay, this is the identifier I'm using. And the input. What are the inputs you are using? Input, clock, reset, insert. Okay, and input. As this is multiple bit, I need to again initialize input. So how many bit? 4 bits, 3 down to 0. I'm using a vector 3 down to 0, parallel in. Okay, parallel in. Okay, and next output reg 3 down to 0, 3 down to 0, parallel out, parallel out. Okay, semicolon. So always at the rate passage of clock, always at the rate passage of clock, passage of clock. If reset, if reset. Okay, if reset, what you will get? Parallel out, parallel out equal to what? So you are initializing the output of all the registers to 0. That means 4 tick binary 0000. Okay, 4 tick binary 0000. Or else if load. Okay, so one more input will be there. So input one more input is there. If load, if load, so here I will keep one more input load. Okay, so here I can use one more input, that is load. Okay, if load, that means if load equal to 1, if load, so parallel out. Okay, again use non-blocking statements. Okay, parallel out is we are getting parallel in. Okay, and end module. Here what I am doing, at a time I am inserting 4 bits of data, and at same clock cycle I am taking out the 4 bit of data. If load equal to 1, so you are sending you are taking out the 4 bit of data output at the parallel out. Okay, so like this we can do the SISO, SIPO, PISO, PIPO. Okay, serial in serial out, serial in parallel out, parallel in serial out, and parallel in parallel out. Hope you understood. Okay, thank you.